Welcome back. So moving ahead to the last part of the robot statics, today we'll discuss kinetostatics measures for robot design and its selection. Apart from the performance characteristics that we have discussed earlier in module 1, these measures will allow us to compare different robots based on the optimum workspace that a robot can offer. Okay, so let us begin with today's module. So yes, let me just introduce you with a small day-to-day problem that we normally handle. Okay, so one such activity that we do normally is cycling. Hope you remember how you do cycling. So you see, you your leg when it is acting on your pedal, it is something very much similar to a 2 degree of freedom arm that you have worked out earlier. So if this is your foot, okay, this acts on the lever, that is your pedal. Okay, this is, if I consider this as link 1 and this as link 2, this is your joint 2, this is your joint 1. Okay, so this is theta 1, this should be your theta 2. So it is very much similar to your 2 degree of freedom robot arm, which is mounted like this. So you see, you are applying pressure over here, which is your pedal, that comes here. Okay, so and you have to push it downwards when your pedal is somewhere like this and you are pushing it at this location so that you can make it rotate like this. Okay, so you require maximum amount of force over here, whereas when it is almost like vertical, you don't want to push it further down, rather you want to make it go like this, is it not? You want to make it go like this so that it keeps rotating like this. Okay, this is your pedal structure, I tell you. So red one is your pedal structure. Okay, so this is the place where you want maximum force, whereas this is the place where you want maximum velocity. So these are two things that is normally handled by the robot also. It has to pick up weight or it has to move. So these are the two things that it encounters most of the time. So you see, even with your leg, so if you are oriented like this and you want to move this pedal, two things are required. So you want your robot to work best in these two parameters, that is force and velocity. So you need to find out an optimum workspace where you should see this velocity which is maximum as well as force which you can put best. Obviously velocity will be maximum best at certain location, whereas force will be best at certain location. So there is some optimum workspace within the robot workspace where you have best that is required for that particular application. So this is just a pedaling operation that we do, and you see maximum velocity is at fully stressed condition along horizontal direction and maximum force is at fully stressed condition, that is along vertical direction. So that is one application. Okay, similar is another application. So you want to build up your body, right? So when you go to the gym and you want to exert maximum, you put your arm fully stressed, okay, where you have to apply maximum amount of effort to maintain that position. So that is the maximum effort that you are applying. So your body can apply least amount of force along this direction when it is fully stressed. Okay, so this is a typical gym sort of application. So your robot, when you have a robot in a workspace, so your robot end effector should work in a region where you have optimum performance in terms of force as well as velocity. So there are measures which can measure this mathematically. So where is your best location in order to work out numerically and get a value so that you can compare two different robots. So that is what we'll be doing in this module. So hope you understand using these two examples. Much better explanation is there with mathematics. So yes, kinetostatic measures for robot design also. Same is used for the design as well as when we select any robot. So dexterous robot. that is quite often you must have heard a robot is dexterous. What it is actually? So ability of a robot arm to reach to all the points within the workspace with all possible orientations of its end effector, okay, and can transmit motion and force, that is the velocity and force, comfortably. So robot should be comfortable when it is working for motion or even to apply certain force, okay. So that is what is a measure. So how will we measure it mathematically? There are terms, there are many terms. Over the years many similar terms have come forward through different researchers. So one by one we'll discuss some of them. So dexterity and manipulability, WD and WM, are quantified by a value given as WD is equal to determinant of Jacobian. J is Jacobian over here, whereas manipulability is given as JJ transpose. Determinant of that, square root of that will give you WM. Both are effectively the same. Okay, if you work out for a regular robot with 6 degrees of freedom, when determinant is 6 cross 6, so this becomes equal to this, is it not? So for a non-redundant robot, J is a square matrix. In that case WD is equal to WM, whereas for a 7 degrees of freedom or more, so you may have to use this one where JJ transpose becomes a square matrix and you can still find out your manipulability. So both are equivalent terms, okay, that are used in context to robots to find out the manipulability. So which one is best? Higher is best or lower is best? So that is what we'll see now. So yes, there is another very similar term. So you see, when you are at fully stressed condition, when you could apply maximum velocity and minimum force, that is one case. There is inner position also when it is fully enfolded. In that case you can apply velocity in other direction, whereas you cannot apply forces in one direction. So yes, both are orthogonal normally. We'll see it mathematically also. So both the positions were singular, you see. So that is, there is a number which is known as a condition number. It is the ratio of maximum to minimum singular values of a matrix J. So we are using J over here because J is something that relates velocity also. V is equal to J theta dot. If you remember, this is Cartesian velocity at the end effector is related using this. Similarly, forces are also J is equal, tau is equal to J transpose of force at the end effector. Tau are the joint torques. Okay, so that is something which is relating the forces as well as torque that goes at the end. So we are using J over here. We'll try to formulate it more better now. So for now you just take it, J is the measure that can give you that. So determinant of J used to give me this one. Now determinant, if it is close to singularity, you know you cannot relate these two, okay, because in order to find out theta dot you have to find inverse of J and you can do this. So inverse is possible only when J determinant is possible. If it is close to singularity you cannot do this, your robot gets stuck. If at all you are using any control algorithms, so definitely that uses this and your robot gets stuck. So that is known as a mathematical singularity. So condition number is a measure that measures how close your robot is to the singularity, okay. It should not be singular. So closeness of a pose to singularity, that is what is measured by condition number. And whether a robot is dexterous, dexterity of a robot is also measured using this condition number. Okay, so these parameters are very, very important. So manipulability is the capacity to change the pose of the end effector of any robot at any given joint configuration. It is measure of how close a robot to the singularity again. Okay, so that is what is dexterity, manipulability, and what is condition number. So you now know very closely these things. Okay, now let us move ahead and try to formulate it more mathematically. So end effector velocity, not just velocity, as well as the torque at the joint are given by these two relations, which are this. What is J? J is a function of theta. It is known as Jacobian. You know that already. Whereas VE and FE are end effector forces and velocity. They are m dimensional real numbers. Okay, so that is given by, it is set of this, and similarly theta dot and tau is n dimension real number, so it is element of this. So yes, again it is depending on n. The n is degrees of freedom, that is number of joints a robot has. So Jacobian of theta, that is a function of theta, is r m times n. It is m times n, that is your J. Okay, that is the dimension of J. Okay, so if at all you want to study the effect of joint velocity, maximum possible combinations of joint velocities, okay, which can give you different kinds of end effector velocities. So let us say you have a 2 degree of freedom to begin with. So it gives you this particular combination, which is very, very useful in studying robot behavior in terms of velocities. So let us say you have theta 1 dot, theta 2 dot, which is plotted in a unit circle, which is given by this. So theta bold dot will be an array of theta 1 dot and theta 2 dot. So this is what it is. So if you say theta dot like this, so it is nothing but theta 1 dot square plus theta 2 dot square is equal to 1. What is that? This represents an unit circle like this. What does it has actually? If at all you have set of points which lies on this unit circle, so you see you have different combination of theta 1 dot and theta 2 dot. So all the directions of theta 1 dot and theta 2 dot is under study with a certain value that goes on this radius. So you see it has both positive here, positive and negative here, okay, and negative here, and positive negative, like that. So you have all the combinations of theta 1 and theta 2. So this can be a very good combination to study the effects. So this is why it is chosen. So you see, if you substitute this over here, so you have just written as theta is equal to J inverse of end effector velocity, all are vectors. Got it? So I substitute that here and here as well in this. So I get this. Moving further, this can be written as this. Moving further ahead, you can write it like this. So you have what? You have VE transpose, VE is equal to 1. In between you have JJ transpose. So what is that? This is equivalent to a ellipsoid equation. I'll tell you how. So this gives me a relation which can be explained geometrically also. But yes, over here, if it is a 2-dot planar robot, it tells you a circle. If it is a 3 degree of freedom robot, so it gives you a sphere. For a higher degree of freedom robot, so it gives you a hypersphere for n greater than 3. And similar is the case over here. This gives you an ellipsoid, or a higher dimension ellipsoid. So both are similar. So yes, so if I can write it like this, VE transpose A inverse VE is equal to 1. So A is nothing but JJ transpose. This is M cross M, that is a square matrix which is invertible also. So yes, in generic case, mathematically, if I say it is X, so I can write it as X transpose A inverse X is equal to 1. A is JJ transpose, which is symmetric positive definite matrix. Okay, so eigenvalues of A is lambda 1, lambda 2 till lambda n. Similarly, eigenvectors are v1, v2, vm. So these are eigenvalues and eigenvectors. So effectively this equation represents a three-dimensional space that represents an ellipsoid. So basically this equation represents a three-dimensional ellipsoid in space. Okay. If it is a 3-DOF robot, remember that if it is a 2-DOF, it is an ellipse, it is n degree of freedom, so it is something very much analogous to that, is extended that in a n-dimensional space. Okay, so manipulability ellipsoid, it looks like this. So you see lambda 1 square root, lambda 2 square root, lambda 3 square roots, they are nothing but axes of this ellipsoid. Okay, this is a mathematical relation, it has got not much to do with robotics. So this expression can relate a similar space in mathematics, which over here, if I say it is VE, it is velocity ellipsoid. If it is a force, it becomes a force ellipsoid. So I'll tell you how and how they are related also. So this is what you have to understand here. So these are your eigenvalues that goes here. Okay, and if A is equal to JJ transpose inverse, over here A was this, if it is JJ transpose inverse, X is equal to FE, it gives a force ellipsoid that results from a unit sphere of joint forces and torques. So just now we have considered joint velocities. Okay, now I have to consider joint forces and torques, and I can use the relation which was here, that is tau is equal to J transpose of F. F is a end effector forces. So end effector force, joint torque and force that comes here, if I use that over here in this equation, so you get to a similar one which will give you ellipsoid of force. And you see both are orthogonal to each other. If velocity ellipsoid is like this, force ellipsoid will be like this. So now I'll compare both of them, manipulability and force ellipsoid, that is velocity and force ellipsoid. So a circular shape of that would mean that end effector is equally manipulable in all the directions. So that means if at all this arm is fully extended like this, the shape of this is something like this. Somewhere in between it will have shape which is something like this. Over here it becomes very much like this. Okay, the shape of this manipulability ellipsoid, it becomes like this. Okay, so it can only have velocity in this direction. Over here it can only have velocity in this direction. Over here you can have velocity in this and this direction equally in both the sides. Okay, so that is what is change in velocity ellipsoid size when it goes from here to here, these two locations. Okay, the circular shape is something that is very much desirable. It is the workspace of this robot where it works best. You can have velocities, equal velocities in almost all the directions. So it is known as equally manipulable in all the directions. This defines the end effector motion capabilities and captures how close the robot is to singularity. If at all you see this or this, that is at the end and at the outside, complete outside and complete inside boundary, so it is almost singular, you know. So this also captures that essence. Okay, so that is what is here. And force ellipsoid, if at all it is shaped like this, this will be orthogonal to this. Okay, with the same principal axes. The size of principal axes will be same. The principal axes are reciprocal to each other also, and the force ellipsoid has a major axis orthogonal to the manipulability ellipsoid. Okay, so you see if this is like this, this has to be like this. So you can apply maximum force in this direction, that means you have minimum velocity in the same direction. Okay, so that is what is manipulability and force ellipsoid. You see there are various examples that I have given here for a 2-arm manipulator or a robot arm you call it. So there is some kinetostatic duality, it is known as. So you see both are directed in this way. So one of them, you see, if it is fully extended, in this case it is like this. You cannot have motion along this direction further, only you can move in this direction, whereas you can only apply force along this direction. Okay, you cannot apply or a minimum force that is applicable in this direction when it is oriented like this. So it is one situation which is shown here, and similar one, you see, end effector force ellipse, it is directed orthogonal to each other. So for the same two situation as it was here, so this time it is directed orthogonal. So in case of force it is directed like this, in case of velocity it is like this. Okay, so this is just an example. So you see, you should expect something like a ellipsoid if it is a 3 degree of freedom system. Even for a 6 degrees of freedom system, it has two partitions which are there. It can be linear velocity, it can be angular velocity. So three for velocity, linear translation velocity, and 3 for angular velocity spaces. It will have Jacobian will be 6 cross 6, you know, in that case j omega and jv are there, you know that very well. ei cross aie. So this part was taking care of angular velocity component, and this part was taking care of linear velocity component. So for even a 6 degrees of freedom robot, so you get to see angular velocity ellipsoid and linear velocity ellipsoid. Okay, so that is what is the case if it is a 6-DOF robot. So at least for 6-DOF it is quite trivial and almost easy to understand, but if it goes very high, it becomes a hyperspace. In that case it is difficult to visualize it geometrically, but idea remains the same. So yes, there are many other manipulability measures which can measure the performance of a robot in terms of kinetostatic measures. So one of them is manipulability measure 1, that is ratio of longest to the shortest axis of that ellipse. So it is given by mu. So it is lambda max by lambda minimum of A. Okay, for that, you know, this is nothing but eigenvalues. So square, that is nothing but axes of your ellipsoid, that is given by square root of lambda, that you remember just now I have shown you. So it is a ratio of those two. If it is greater than 1, so that is what is manipulability measure. Normally it is greater than 1. Yes, it should be. If it is equal to 1, that means it is equally manipulable in both the direction. So you can have various notions to this for various values of this. Okay, so if mu is 1, it is known as isotropic and it is equally manipulable in all the direction. Higher value would mean that robot is more close to the singularity. If the value is very high, you know, lambda max, if it is maximum, other side is minimum, that means it is robot is almost singular. Okay, so just now you saw that by examples of a 2-hour robot. So geometrically it is easy to visualize at least. Okay, for there is another manipulative measure, that is a condition number. It is nothing but mu square. So you just have to take square, and this also has a similar meaning. It is known as a condition number. Just now we saw the definition of that. So it also measures how close it is to the singularity. So these definitions have evolved over years and given by different researchers parallelly at different instance of time. So yes, there is another very good measure, that is proportional to the volume of the ellipsoid. If you remember, volume of the ellipsoid is given by lambda 1, lambda 2 and product of all the lambdas that you can get. So if it is taken square root of that, what you get is something this, and it is nothing but volume of the ellipsoid. For in case of a 3 degree of freedom system, it is easy to visualize. So let me just show you that figure. So it is this one. So you see this into this into this, it is nothing but it is volume of this ellipsoid. Got it? So mathematically it is given. It has got not much to do with robotics here. So that is what gives you the volume of the ellipsoid. So if it is higher is the better, so that you understand higher why it is better, it is closer to sphere. So if it is near to ellipse or stressed ellipse, so volume becomes very less. Okay, so you have less manipulability. That means it is very near to the singularity also. Okay, so if it is a sphere, volume is maximum, so that is the best situation that you want. Okay, so maximum volume occurs when axes are equal and it is a sphere. The robot can move with equal velocity in all the direction. Same will be the situation for force also. It will apply equal amount of force in all the directions. Okay, so that is what is very good physical meaning out of something which is mathematics here. So if the volume of a manipulability ellipsoid becomes large, the volume of force ellipsoid becomes small. Okay, so that is again it is true mathematically. So yes, in case of a higher degree of freedom robot like 6-DOF system, as just now I have told you, it is j omega and jv. J omega is again 3 cross n. So it is angular velocity and moment ellipsoid that you will get out of it. Jv, if you use jv, you get linear velocity and force ellipsoid. Okay, so these are some of the measures with which you can measure the performance of the robot. Kinetostatic performance characteristics, you can say. Okay, so with that I'll end here, end this module also. So in the next module we'll start with dynamics and we'll do dynamics of various robotic systems, basically serial robots that we are dealing with. So that's all for today. Thanks a lot.